In this episode of Module 2, we're going to define heat as we know it. And heat is something that we all kind of understand in a way and appreciate it. But that sort of natural approach of defining heat is not adequate for our experimental purposes. So what we're going to do is define heat in a very systematic manner so we could determine the heat produced or heat released in a given experiment. And that's the goal. And so we will ask the question, how do we define heat? We define heat by the following statement. It's a quantity that appears at the boundary of a system during a process. And the heat that appears at the boundary is then absorbed by a mass of water, and its temperature is increased by 1 Kelvin. And so we measured and reported and defined the temperature, and we defined surroundings, we defined the system. So now we're defining heat as certain property of the system that appears at the boundary during a process, and then it raises the temperature of water in the surrounding by 1 Kelvin. So this is a very straightforward, practical way to define heat. This doesn't necessarily mean it has to be water and in the surrounding. It does not necessarily mean you got to have 1 Kelvin rise in the temperature for us to call something as heat. But is a method, practical way of determining heat generated in the surroundings. The reverse is also possible. We'll talk about that. So we give the symbol Q for heat. And the sign for heat is negative when water in the surroundings is heated, or the system is losing certain quantity of heat to the surroundings. It's positive when the system gains heat, means the water in the surroundings giving up some heat and the system is gaining that heat. And so here is an example of an object put into a water bath, and it has certain temperature, bath temperature of T0, and a certain process is carried out. Could be whatever process it may be. And then at the end, the temperature of the water in the water bath has been increased by 1 Kelvin. And so we can now calculate the amount of heat that appeared at the boundary of the system when the process has taken place. So you do this by simply measuring the temperatures, initial and final, measuring the mass, measuring the specific heat of the water that has been equilibrated. So let M be the mass of water in grams, and S be the specific heat of water. Then Q is equal to minus M times S. Now remember, we made sure the change in temperature is just 1 Kelvin. But that need not to be the case. It could be certain value delta T, changing temperature from T1 to T2, and we can readily replace the above expression in terms of T1 and T2 in the following way. So Q then equals to minus T2 minus T1, final temperature minus initial temperature, multiplied with the mass of water M and the specific heat of water S. So one would ask then, why is there is a negative sign? The negative sign ensures the sign that we defined earlier. That is, if T2 is larger than T1, then T2 minus T1 is a positive quantity, mass is a positive quantity, specific heat is a positive quantity, therefore Q is negative. So whenever there is a raise in the temperature of the surroundings, certain heat is being released from the system into the surroundings, so the system lost certain heat. So it has to be a negative quantity. So this is the reason to put the negative sign. T2 minus T1 gives the delta T, change in the temperature, and M is the mass, S is the specific heat. So this is how we make a measurement of heat. And so by measuring the temperature of water in the surroundings, we can measure heat changes. Temperature of water in the surroundings, so Q and T are not equivalent quantities. This is really important to understand. It's a clear distinction between the heat and the temperature. Q is calculated using temperature. We defined temperature in the previous snippet. The units for Q are calories, joules, etc. Heat flows from high temperature to low temperature in a spontaneous way. This is our experience. We ask the question why. And we'll come back to this question again and again. But this question is posed at this time to demonstrate that heat and temperature are different, distinct quantities. And we also would state, since we are discussing heat, all forms of energy can be converted completely into heat. This is a general observation. You can take a mechanical energy and you can convert that into heat. So grinding of a stone on the top of a stone, the mechanical energy is being spent, and then at the end of the day, the stones get warmed up. So we can convert the heat into, you can convert mechanical energy into heat as a Joule's mechanical equivalent of heat law. And we can also use electrical energy, heat, a bucket of water, and you can convert completely the electrical energy into heat. Same with any other form of energy. This is why heat is a very special type of energy, because you can convert any form of energy into heat. But converting heat into other forms of energy is not 100% efficient, can never be 100% efficient. So the converse is not necessarily true. And so this is something we address in thermodynamics. That's exactly what it means. The word thermodynamics means the dynamics of heat. We can convert any form of energy into heat completely with 100% efficiency. But converting heat to a given type of energy is less than 100%. And that conclusion comes in later on, you will see in thermodynamics. But the science of thermodynamics examines the interconversion of one form of energy into heat or heat to another form of energy. This is usually how the thermodynamics is developed and understood and orchestrated. And it's important to remind ourselves that heat always manifests at the boundary during a process. Okay? Summary. Heat manifests at the boundary of a system. Heat is quantified by monitoring temperature of water surrounding the system. Mass of water, specific heat, delta T are the variables. Heat is produced or consumed only during a change. There is no change, no heat produced or absorbed. This is really important to understand it. The sign of heat is negative when the system loses heat, and it's positive when the system gains heat. So these are the important attributes we need to remember and keep really good track of.